The first section we're going to cover today is section 2.2 on separable equations. You're going to find that this is a very clear extension of the techniques you were learning in Calc 2. So there's no universally acceptable method for solving the general first order equation when it is nonlinear. So we've already looked at solving with direction fields, which we're not really going to be doing in this class. And then we were also talking about a certain subclass of first order differential equations that we can solve with direct integration. So we call them separable. So we're going to be focusing on these separable equations. It's when we can put a function of y with the y prime on the left and a function of x on the right, and then we can integrate both sides. We can also write this as a function of x plus a function of y equals 0, which is kind of cool and will lead us into exact equations, which we will be studying next week. So let's look at some examples. So let's solve this following equation. This is from section 1.3. We looked at a direction field for this one, and this one I believe was the one that was concentric circles. So let's see if we can solve this separable equation. So this one says we've got y prime equals negative x over y. So let's start out by saying that's a dy dx equaling negative x over y. If we multiply both sides by y and dx, we end up with y dy equals negative x dx. From there, it's as simple as integrating both sides. And once we integrate, we find out the integral of y is 1/2 y squared. And we can just combine the c's on the right-hand side. And then the integral of x would be negative x is negative 1/2 x squared plus c. We'll just use the 1 plus c on the right. So now we can actually bring over the x squared to the left, and we have an equation that looks like 1/2 y squared plus 1/2 x squared equals c. And if we multiply the whole thing by 2, we end up with x squared plus y squared equals c. And what that is the equation of a circle. So this is exactly what we found when we did the direction field. So this would be a family of solutions that are concentric circles where the radius is the square root of c. So it's kind of cool. This problem looks a little more complicated. So here we have a function of x and a function of y on the left, and our derivative is on the right, also with a y. So first things first, I like to rewrite it where I have all of the derivative on the left. So I'm going to make it y dy equals x plus, dy dx equals x plus 1 times y squared plus 1. And now let's put all the y's on the left and all of the x's on the right. So we would end up with y over y squared plus 1 dy on the left, and it equals x plus 1 dx on the right. So what's really cool here is that when we integrate now, on the left, it's going to have to take a little bit more work than the right. So on the left, we have y over y squared plus 1. If you need to use u substitution here, you can. You can say let u equal y squared plus 1, because then du dy equals 2y, or du over 2y equals dy. So if we did a substitution then, we could say that this was the integral of y over u times dy, which is du over 2y. And on the other side, we just need to integrate x plus 1, which will be 1/2 x squared plus x plus c. On the left, we find out that those y's are going to cancel out, and we're going to be left with the integral, or 1/2 the integral of du over u, equaling 1/2 x squared plus x plus c. Well, that's simply the natural log of u. So we end up with 1/2 the natural log, the absolute value of u, equals 1/2 x squared plus x plus c. And now we plug back in u, which is y squared plus 1. And I'll probably multiply the 2 through. So let's make it the natural log of the absolute value of y squared plus 1 equals x squared plus 2x plus c. So now all we really need to do is solve for y. So that may seem like a very strange thing here. And that's because we need to explicitly. So when we say an explicit solution, that means that we're solving for y. So that's what we're going to do for this one. What we did on example problem 1 was an implicit solution. And that means that that was where we had like x squared plus y squared equals c, instead of y equals the square plus or minus the square root of c minus x squared. So we could have solved for y, but we didn't. An explicit solution is literally solving for y. Implicit means simply that we're not going to bother doing all the extra algebra. But in this case, we want an explicit solution. So let's see where we need to go from here. So from here, we've got the natural log on the left. So we'll make it a power of e. So we'll end up with y squared plus 1 on the left. And on the right, it's going to be e to the x squared plus 2x plus c. So we end up with y squared plus 1 equaling, let's see here, sorry, I screwed that up. Let's just bring the 1 over. Go ahead and do that. So y squared equals e to the x squared plus 2x. And then again, remember how we said before, we can make that e to the c times e to the c, and then we'll take away the 1. And remember we said before that e to the c can simply become c. So we can then solve for y by taking the square root. So y is going to be the plus or minus square root of, now we can move that c to the front, e to the x squared plus 2x, and then minus 1. So this definitely brings in a lot of the concepts that you were looking at in Calc 2. This next one is going to require a topic from Calc 2 that you're probably not going to be that excited to go back and revisit. However, we're going to be using this particular concept over and over and over again in this class, so it's good that we bring it up quickly and remind ourselves how it works, and that's the concept of partial fraction expansion. So we're going to need that in this problem, and we'll see why shortly. Because here, we've got y prime plus x times the quantity at y squared plus y equals 0. So we need to move all the y's on one side and the x's on the other. So in that case, we would have dy dx equals negative x times y squared plus y. So on the left, we're going to get 1 over, well, y squared plus y, we can make y times y plus 1. And on the dy, and on the right, we're going to just have negative x dx. So clearly, we're not going to be using partial fraction expansion on the negative x, so that we can find that integral. So the integral that we're going to have to use it on is on the y's. So let's set it up. Let's look at our partial fraction expansion. We'll call it PFE over here. So what we know is that we've got 1 over y times y plus 1. And that came from something we'll call a over y plus a b over y plus 1. So what we know then is if we find the common denominator on the right, we would have a times y plus 1 plus b times y, and it would have to mean then that it's over y times y plus 1, so to set it equal to the other side, it would simply have to equal 1. So in that case, we end up with ay plus by plus a equals 1. And this is the part where you might remember it from Calc 2 and you might not, but you have to set like coefficients equal to each other. So if we look at y, I've got a plus b. But on the right-hand side, I have no y. So I'm going to write it out. So in terms of y's, I have a plus b equals 0, which tells me that a is negative b. Then for the coefficients, find a different color here to highlight, I just have a and it equals 1. So we actually already know then that for our coefficients, our constants here, we have that a equals 1. Well, if a is 1, then 1 equals negative b, so then b is negative 1. So now that we know that 1 over y times y plus 1 can be written as 1 over y plus negative 1 over y plus 1, we can replace that in our integral. So let's do that. So now we're going to have the integral of a over y, so a is 1, so 1 over y. Luckily, we know what that integral is, which is going to be the natural log. And then we're going to have minus 1 over y plus 1. And that's going to be another natural log. And on the right-hand side, we're going to have negative 1/2 x squared plus c. So now we end up with the natural log of y minus the natural log of y plus 1 equaling negative 1/2 x squared plus c. So if you remember the rules of logs, then we can put this together as the natural log of the absolute value of y over y plus 1 equaling negative 1/2 x squared plus c. And again, we pull our same trick, make both sides a power of e. So we end up with y over y plus 1 equaling c e to the negative 1/2 x squared. And I jumped ahead a little bit by remembering that we can change this c becomes e to the c, which we can then become c. So now that we have y over y plus 1 equals c e to the negative 1/2 squared, we can go back now and we can plug in our initial condition here. So we were given y of 2 equals 1. So let's plug in y of 2 equals 1. So y of 2 equals 1. And that tells us that 1 over 1 plus 1 equals c e to the negative 1/2 times 2 squared. Well, 2 squared is 4, divided by 2 is 2. So we end up with 1 over 2 equals c e to the negative 2. So what we end up finding out is that c is 1/2 e squared. So now that we know that, we're going to have a little bit more work to do. So now that we know that c is 1/2 e squared, we end up with, here, I'll switch back to purple. We have y over y plus 1 is now equal to 1/2 e squared, e times e to the negative 1/2 x squared. Which means we can also rewrite this as 1/2 e to the 2 minus 1/2 x squared. We can simplify our lives a little bit. But this is where things get interesting, because if we want our explicit solution, we're going to have to multiply both sides by y plus 1. So if we have y is now going to be 1/2 e squared, or e to the 2 minus 1/2 x squared, times y plus 1/2 e to the 2 minus 1/2 x squared. So what happens now is we have to subtract this term with a y on it back over to the other side. So this is really just a whole lot of algebraic manipulation just to solve for y. So when we pull it back over, we get y minus 1/2 e to the 2 minus 1/2 x squared, y, and it's going to equal 1/2 e to the 2 minus 1/2 x squared. So now all we have to do is factor out the y, and we end up with 1 minus 1/2 e to the 2 minus 1/2 x squared equals 1/2 e to the 2 minus 1/2 x squared. So now when we divide it through on both sides, we end up finding out that we have y equals, now remember we have a 2 in the denominator over here. So we can put this expression from the left with the 2 in the denominator. So we're going to end up with 1 times e squared, or sorry, e to the 2 minus 1/2 x squared over, and we'll leave the 2 there, and then we have 1 minus 1/2 e squared minus 1/2 x squared. So if you distribute that 2, you can simplify this y just a little bit more to e to the 2 minus 1/2 x squared over 2 minus e to the 2 minus 1/2 x squared. So that would be our explicit solution. A whole lot of algebra to get down to this explicit solution. I believe there are a couple of these in either the written homework or the online homework on WebWork that you're going to have to do, where you have to find the explicit solution. They're never really nicely rounded or anything, because in real life, especially with all the models we've looked at, it doesn't fit into, like, let's just use whole numbers. Let's use very easy algebraic expressions. That's not how natural phenomena occur. So we often find that our solutions can get very, very messy. Let's try this last one. I'd like for you to pause it here and try it on your own, and then come back and see if you got the same answer. Okay, so hopefully you tried this one, and I'm hoping that you found this one a lot more approachable than the last few have been. So for this one, we're already in dy dx format, so really all we have to do, the expression with y is already in the denominator on the right, so literally all we have to do is copy that to the left and just multiply both sides by 5y to the 4th plus 1. So we end up with the integral of 5y to the 4th plus 1 dy. That's not going to be equal to the integral of 2x plus 1 dx. And this is much simpler than all the other examples we've looked at. We end up with a y to the 5th plus y on the left and an x squared plus x plus c on the right. So now, again, we have y of 2 equals 1. So let's plug in y of 2 equals 1. So we end up with 1 to the 5th plus 1 equals 2 squared plus 2 plus c. So we get 2 equals 6 plus c. So negative 4 equals c. So we end up with y to the 5th plus y equals x squared plus x minus 4. Now the question here is, can we find an explicit solution? And the answer is no. You cannot get the y by itself here. So you're not going to be able to find an explicit solution. So the only thing left in this section to discuss are the homework problem. So I gave you one initial value problem that I created and 4 problems from the book, and these are all practice. I did not assign all of these problems for the homework to turn in for homework 2. I think it was only problems 5 and 23 if I remember correctly. So just so you know, but there are more there for you to practice, and you should have solutions to these. At least the final solution should be in either the Student Solutions Manual or in the back of the textbook.